Concept 2, assessing the line of best fit. When we are looking at graphs or scatter plots that have lines of best fit, and we're comparing the two, we're trying to figure out which fits the data better, right? Which line is a better match, which can help us predict future events or different values better than the other. What we're really looking for is which line has points on the graph closer to it. Okay, the closer the points are, the better our line is, the better our line of best fit is. So we can see pretty clearly that this one has points really close to the line, all right, very close, and this one has points much further away. All right, so this would be our better line of best fit. Okay. For this one, you can see the little red lines here. When we're calculating line of best fit, and we're not going to be calculating it, we're just going to be looking at it, observing it, and making a judgment on which line is better. But when you do get to calculating it next year, you're going to use the vertical distance to do that calculation. So that's what those red lines are. They're calculating the vertical distance away from the line of best fit to help figure out just how good a fit for the data it is. Okay. The other thing we're going to be doing with our lines of best fit is when we see them on a graph, all right, it's often easy to say, okay, well, this looks pretty close. We've got a whole bunch of data. It's fairly close to it. It's not bad. It might not be the strongest data. This might be a little bit stronger. But one thing that's hard to see is, okay, what's my value going to be? What's this value going to be? What's my y value going to be when x is, 35? When it's way over here. It's not even on the graph. Okay? And to do that, we are going to need to figure out the equation for this line, or at least estimate it. Okay? Because sometimes these equations are really pretty weird, right? They're not nice, even numbers. So we're going to be estimating it. Okay? And the best way to do that is to start, if you can. Sometimes you can't, but usually we will be able to. Start by finding the y-intercept. Okay, y-intercept here. And to me, I'm going to say that is, I'm going to say 13. Okay, so the y-intercept for this line is 13. Okay, and then we've got our y-intercept. The other thing we need to get a slope-intercept form equation is the slope. So I'm going to need to find another point on this graph. And I might look until I see one that I think, exactly lands on an intersection, but I'm not seeing any that I can be super exact with, so I'm just going to use this. I'm going to say that this point to me, here at 5, looks like it is at about 18. Okay, it's about 18. All right, so I've got one point at 5, 18, and another point at 0, 13. Okay, so I'm going to take those values, and oh shoot, I made a mistake. Not 518, 528. That would have been bad. 528 and 0, 13. Okay, so those are my 2 points, and I'm going to use my slope formula. Okay, remember y1 minus y2. I'm going to make this point 1. I'll make this point 2. That'll be easier. Point 2, and this will be point 1. Okay, so y2, 28 minus y1, which is 13, over x2, 5 minus 0. Okay, 28 minus 13 is 15, over 5 minus 0 is 5. 15 over 5 is equal to 3. So my slope is 3, my y-intercept is 13, and my equation for this line of best fit I would estimate as y is equal to 3x, 3x plus 13. Okay, and that would be my equation. All right, I do the same thing over here. My y-intercept is 35, and this one looks pretty good. I don't have to estimate it. My y-intercept is 35. And then, you know, it looks pretty close to be coming down, 5 and over 12, but it's not quite there. Okay, each block is 12, and each block in the vertical distance is 5, but it looks like it's coming down a little more than 5 for every 12. So I'm going to need to do the same thing. I'm going to need to estimate a value, and maybe I'll go right here and I'll say that this, where it's 60, is at 8. Right? So I've got 60 and 8. And here I've got 0 and 35. Okay. And just looking at this graph, I know that my slope is going to be negative. Okay. But I'll still set it up. We'll do 0.2 and 0.1. So x2 is 8 minus 35. Or sorry, y2. X2 is 60 minus 0. All right. If I do my subtraction, I'm going to have a negative 27 over 60. All right. And that's pretty ugly. I can simplify that. Divide both sides by 3, or both top and bottom by 3, and I would get a negative 9 over 20. Okay, still going to be fairly ugly. If I have this as a decimal, it won't be too bad, but it's still not going to be something that I can easily look at and say, okay, that's like a slope of 3. All right, but this is going to be pretty common for estimating these slopes, right, or estimating our lines. Okay. But I've got my y-intercept, I've got my slope, so my equation is going to be y equals negative 9 over 20 times x plus 35. Okay, and that's fine. And maybe this actually is closer to 1/2 or negative 1/2 or something else, and I've made a mistake. But that's okay, because we're just estimating. We're trying to get close, and if we're not quite there, it's okay if we're a little bit off of our actual equation. Okay, because we're looking for something that can estimate values for something that's not on our graph.